So we've been talking about RISC-V assembly instructions, and today we're going to start talking about how we encode these into bits. So this is the real power of the stored program. So a program that's stored in memory is 32-bit instructions and data are both stored in memory. So we can have a sequence of instructions that tells what the program is supposed to do. The only difference between any two applications is really just the instructions. So to run a new program, we don't have to rewire anything like we have to do in hardware. We simply store a new program in memory and then begin executing that program. So program execution, the processor fetches or reads instructions from memory in sequence. So one after the other, instruction 1, instruction 2, and so forth. And the processor performs the specified operation. So here's an example program. We have the assembly code here on the left and the machine code on the right. We're going to talk about this right now, how we encode those instructions into a 32-bit binary number. But the PC, the program counter or PC keeps track of the current instruction. So in this case, the PC would be equal to hex 20. So it keeps track of the address of the current instruction. So it starts with the first instruction, this add instruction, which is encoded like this. We'll talk about that in a moment here. But it starts like that, and then PC increments after that add instruction is completed, and increments to hex 24, so increments by 4s, and PC is now equal to hex 24, and goes to the next instruction, and continues fetching or reading new instructions from memory, and then doing whatever the instructions says should be done. So let's talk about machine language. So machine language is the binary representation of instructions. Computers only understand ones and zeros. Well, we all know why, because they're made of hardware, and you've been doing that, this whole semester. So we're going to use 32-bit instructions because, again, using the principles of good design, especially computer architecture, 32-bit data, 32-bit instructions can be easier for us to deal with. So when we're fetching anything from memory, whether it's data or instructions, it'll be 32 bits wide. So RISC-V has 4 types of instruction formats: R-type, I-type, and the S/B type and U/J type. So these last two really have 2 variations each, and we'll talk about that in a moment. So here's our R-type or register type format. And we're going to have, some fields here. So we can see down here, there are certain fields. We have the RS1 and RS2 fields. Those are source operands or source registers. And RD, here's RD, is our destination register. So D stands for destination. We also have these other fields, and I've highlighted them in blue. The op field, which we call the opcode or the operation code. So the op field or opcode. And we have these 2 other fields, funct7, which is a 7-bit function code, and funct3, which is a 3-bit function code. And together these 3 fields, funct7, funct3, and op, determine what that operation should be. So what operation should be performed by the processor. So here's an example of some R-type instructions. So R-type, remember, stands for register type. So our operands are all in registers. So add is one of those, an R-type instruction, because it only has register operands. And we'll remember from when we first introduced it, this is our destination register, where the result is going to be put, or the destination of the result. And then we have our 2 source operands, RS1 and RS2. And you can go back to that register page to figure out, well, let's see, S2 was register 18, S3 is register 19, and S4 is register 20. So now we're just going to put those values in the different fields. So we put, RD 18, RS1 19, RS2 20. So notice that they go in the opposite order here in the machine code as they do in the assembly code. And so the other fields are, well, it's just determined by the architecture, the instruction set architecture designers. So the opcode for add and turns out subtract is 51. It's a 7-bit representation of 51. And then we have these two other fields, func3 and func7. Func3 is all 0, so it's a 3-bit representation of 0, and func7 is a 7-bit representation of 0 for add. And so we can just look that up and see what those fields are, or here, as I've shown, it's given to you. So then we can do a similar thing with subtract. So here we have subtract, also an R-type instruction. T0 is register 5, T1 is register 6, and T2 is register 7. So we put our opcode in for subtract. It's also opcode of 51. So in order to determine whether it's an add or subtract, we really need to look at then the func7 and func3 bits as well. So func7 is 32 in the case of performing a subtract operation, and func3 is still 0. And then we fill in our registers. So RD is 5, RS1 is 6, and RS2 is 7. So now the common error here is people want to then go just directly from here to the hexadecimal or 32-bit hexadecimal representation, but really you can't. So now going to put those values into binary. So here, for example, for the add, we have a 7-bit representation of 0. We have binary 5-bit representation of 20, 5-bit representation of 19, 3-bit representation of 3, 5-bit representation of 18, and 7-bit representation of 51. So only after we've put them into binary can we then take the groups of 5 starting at the right, or because it's an even number of or an even multiple of 4, we can start gathering bits starting at the right or left, but starting at the right helps you keep the good practice in case there's a non-multiple of 4 number of bits. And so we gather groups of 4 here starting at the right, and here we have 0, 1, 4, 9, 8, 9, 3, 3. So here's our 32-bit representation of this add instruction, add S2, S3, S4. And we do the same thing for the subtract instruction as well. So again, note the order of the registers in the assembly code differs from the order in the machine code. So our second type of instruction, of machine instruction, is the I-type or immediate type, because one of the operands is an immediate. So we have one source operand that's a register, RS1, a destination register, and then an immediate. So this is a 12-bit 2's complement or signed immediate. And then we still have the opcode, so simplicity favors regularity. All instructions are going to have an opcode. That's the first thing we're going to look at to see, hey, what instruction is this? And then we have func3, a 3-bit function code. You'll notice that there's no more room for func7 because that space was taken up by the immediate. Okay, so in this case, in the I-type case, the opcode and the function 3 bits determine what the operation is. So some I-type instructions are add immediate. We have two registers and an immediate. We have the destination register, RD, the source register, and the immediate. And so we can just put our values into the fields. So in the case for add immediate, again, determined by the instruction set architecture designers, the opcode is 19 and the function 3 bits are the 3-bit representation of 0. And then we can go back to our table of what register numbers correspond to S0 and S1. Turns out that S0 is 8 and S1 is 9. You should refer to that chart in the prior slides. So we have X8 and X9, or register 8 and register 9. And so we put register 8 into RD. That's our destination register. And we put the number 9, the 5-bit representation of 9, into our S1. And then we put our 12-bit signed immediate into the immediate field, the 12-bit immediate field. And we can do the same for our different other instructions as well. So we have another add immediate. This one, we'll notice that the signed immediate is negative. Then we also have load word and other variations of loads, load word, load half, load byte. And so here we have our source register, RS1, S3, which is register 19. Again, we look at our chart of the register numbers, and T2, which is the destination register. So where we're going to load the memory address determined by the offset plus the base address, RS1, and load it into register RD. So in this case, T2 is register 7. And now we can do the same thing. So we put our destination register in, register 7. We put our source register, register 19. And then we put our immediate, in this case it's an offset of -6. It's a signed immediate. And for our load word instruction, the opcode is 3, and the function 3 bits, or the 3-bit representation of 2. And you'll notice for load half and load byte, the opcode's the same as load word, just the function 3 bits differ. So the function 3 bits distinguish whether it's a load word, load half, or load byte. And so same thing after this. People sometimes want to go directly from this to the hexadecimal, but you can't. So let's look at this one, for example, this add immediate S2 T1 minus 14. So we'll represent minus 14 in 2's complement and put that in the immediate 11:0 field, so the 12-bit signed immediate field. The value 6, represented as 5 bits. 0, a 3-bit field for function 3. 18, 16 plus 2, and the opcode, the 7-bit representation of 19. Then after we do that, we start grabbing groups of 4, starting from the right, and we can now then read off what the hexadecimal representation of this value is. So it's F, 2, 3, 0, 9, 1, 3. So now we have the 32-bit representation or machine code of that add immediate instruction. So note here, again, the order of the registers. So the order of the registers in the assembly goes RD, RS1, immediate in the assembly code, but notice the fields RD, RS1, and immediate are the opposite way in the machine code. And just note the field. So RS1 is the base address for the load word or load half or load byte instructions, and RD is the destination register, or where we're loading that memory into. So the third type is the S-type instruction. And so the S-type instruction, well, it's actually, so there are two that are very similar, the S-type and the B-type. We'll talk about both those. S-type stands for store type, so this is for store instructions, and has two register operands. RS1, again, just like load word, is the base register, but RS2 is the value to be stored to memory. So remember, in the store word instruction, we have some value in a register that we're going to store to memory. So RS2 holds that value that we want to store to memory, and then we determine, what the address is by adding the offset to the base address. So again, remember, RS1 is the base address. And then we have the opcode and the function 3 bits that again determine what operation to perform. So the S-type instruction is a little bit strange in that the immediate here is split across two fields. It still is a 12-bit immediate, but it's split so that bits 11 to 5 are up in the top 7 bits, and then the lower 5 bits are later in the instruction. Well, why is this? It's slightly annoying, but it's so that we can keep RS2, RS1 in the same place across instructions. So if you'll notice, for our I-type, for example, RS1 is here, and for R-type, RS1 is in the same place, and then RS2 is also in the same place as the S-type instruction. Okay, so let's take a look at some of these. So here's store word. We also have store half and store byte. Just like load word, they're control, so op code and function 3, so telling what the instruction what operation the instruction should perform. The only difference is, well, they all have the same opcode. Now we'll have to look at these function bits to determine whether it's a store word, a store half, or a store byte. All right, so let's look at the store word instruction. Again, remember this is our RS1, our base address, and RS2 is the value that we're going to store to memory. Remember, T2 in this case, this register holds that value that we want to store to, well, this address, -6 plus whatever in S3. Okay, so again, we can look at our table and see the T2 is register 7 and S3 is register 19. And again, our opcode is 35. That's something we can just look up, whereas in this case, I just gave it to you. And our function 3 bits are 2. So now we represent -6. Again, now this is, let's see, well, +6 would be this. So take the 2's complement to figure out what -6 would be. So that's 1, 0, 0, 1, plus 1. And I can sign extend it then. 1 plus 1 is 0, carry the 1, 1, 0, 1, and then I sign extend it to 12 bits. Okay, that's fine. So the lower 4 bits are here, plus 1, so 5 bits. And then the rest, those top 7 bits, are up in that upper field of the immediate. I just fill in RS1, 19, my base address, and register 7 holds the value I want to store to memory, so RS2. And then same thing as before, now I just fill in the fields on the bottom. So, take that immediate field and then represent 7 in 5 bits, 19 using 5 bits, 2 using 3 bits, 1, 1, 0, 1, 0, the lower 5 bits of the immediate, and then 35 represented in 7 bits. And then, grab groups of 4 and blah, 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 and write it into the hexadecimal representation. So the next type is very similar to the S type. It's called the branch type or B type. It's very similar to S type. It's just the way that we're going to handle the immediate fields. So all the fields are the same. We have an RS1, so register source 1, register source 2, and we have an immediate here, a 12-bit 2's complement immediate. It's the address offset. So we'll talk about what does that mean, address offset, in a minute. And then we also have this opcode and function field, function 3. So the fields look very similar. It just, these immediates are kind of odd. So the immediate's actually represents a 13-bit immediate. So you can see the most significant bit is bit 12. And so this is a 13-bit immediate. And let's see why it's 13 bits and what happened to bit 0 and why is it all, we thought the last one was bad where it split the immediate across these two locations or two fields in the instruction. Well, now it's doing a bunch of other stuff going on here. Okay, so let's take a look at what this does. So again, it's a B type, and so it actually encodes a 13-bit immediate, even though it only uses 12 bits in our instruction. This 13-bit immediate encodes where to branch for a branch instruction relative to this branch instruction. So branch if equal here, well, we don't need to know if it's equal, but if it is, we need to know where to branch to. So in this case, we want to branch 1, 2, 3, 4 instructions past the branch instruction, the branch if equal instruction. So there are 4 instructions past that. So here's our label L1 we want to branch to, and that's 4 instructions past the branch if equal. And so this is actually, let's see how many bytes pass. So, right, each of these is stored in an address. Let's say this is address. Let's make it easy, storing in address 0. The next one's address 4, address 8, address C, address 10, or address 16, right? 0, 4, 8, 12, 16 in decimal. This is hexadecimal. And so we want to encode the number of instructions past the branch if equal. In this case, the number of instructions is 16 bytes, so 4 instructions in memory. That's going to be 4 times 4 bytes past the branch if equal instruction. And we want to write that using 13 bits. So let's see. So we have the number 16. So 1, 2, 4, 8, 16. We put a 1 there. And we fill out the rest of them with zeros. So here's our 13-bit value that we're going to encode. 13-bit immediate. But now we're going to do some kind of tricky stuff. So let's take a look. Written nicely here. Here's our 13-bit immediate encoding of the value 16. This is a signed immediate, so it could be a negative. Could have branched, backwards. So L1 could have been up here, add, subtract, or whatever. Blah blah blah. In that case, it would have been -2, right? 1, -1, -2. That would have been -2. That we would have needed to encode in a 13-bit signed immediate field. But in this case, we're going to go back to our original case of where our L1 label is 4 instructions or 16 bytes past the branch if equal instruction. And now we're going to say, well, let's see, this is bit 12. This is bit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So actually we're always going to have, these two are always going to be 0. Those 2 bits are always going to be 0 because, right, 0, 4, 8, C10, blah, 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 right? You'll notice that multiples of 4, those bits are always 0. So I actually don't have to encode either of those bits, but because RISC-V has a version that has 16-bit instructions, we actually don't encode, we don't look at that. We don't ignore both of them. We ignore just the bottom one, the least significant one. So we're not going to encode that one. So basically, it's so that we can use RISC-V instructions for instructions that are 16 bits. So it would be at 0, while the next instruction, instead of being at 4, would be at, basically the half. 0, 2, 4, 6, 8, blah, blah, blah. Right? These are the instruction addresses. If they're 16 bits wide, so 2 bytes. Okay. Ours we're still, this will always be 0 for our 32-bit instructions, but we do encode it. So now we're going to take that and say, okay, well, I'm going to encode all of the rest of these bits in my instruction field. But that's why it only goes from 12 to 1. Well, we know that this 0th bit is always going to be a 0. Turns out the first bit is also always going to be 0, but we encode that to allow for 16-bit instructions. Okay, so we take that, and now we do this other odd thing. We're going to encode, remember, we're ignoring that bit, but we're going to encode the rest of these. But now we do something else that's strange, is we take bits 4 to 1 and encode them here. And then we take bit 11 and encode it here. It's kind of like, moving all the bits around. And then the last thing that we're going to do is take bits 10 to 5. Let's use a different color for that. Bits 10 to 5 and put those here. So these are bits 10 to 5, these ones on the bottom here. It's 10 to 5. And then the last thing we're going to do is take bit 12, this last one, and make that our most significant bit. So in this case, we have branch of equal S0, T5, L1. Again, we're using this code that we just looked at, this RISC-V assembly code snippet. And we're going to encode, well, let's see, S0 is X8, T5 is register 30, and this is RS1, RS2, and then we encode the label as basically how many instructions or how many bytes past the current instruction, past this branch of equal. And so we're going to take our RS1, register 8, RS2, register 30, and we encode our immediate in that strange way that we just talked about. And for branch of equal, the opcode is 99, the 7-bit representation of 99, and the function 3 bits are 0. So again, we write that in all of those in binary, group it by groups of 4, and write that value, that encoding in hexadecimal. Okay, so just remember this is kind of an odd, you really have to write out the 13-bit representation of that offset, and then, kind of bit swizzle like the bits around to figure out, where the bits go. But don't try to, don't do that in your head. Just write down the actual number. So in this case, 4 instructions or 16 bytes past the branch of equal, and then you can do the bit swizzling from there. Right? Grabs bits 4 to 1, and then 11, and then grab bits 10 to 5, and prepend that with bit 12. Okay, so why all these acrobatics with bits? Well, we'll look at all of the instruction encodings together at the end here and see why this choice might have been made. Certainly, it's not for our benefit or for the compiler's benefit. We're actually at this point going from assembly to machine code as the assembler, this is certainly more confusing. But we'll see that this is actually for hardware to make the hardware simpler. Okay, so the next type of instruction, well, the next two types, they're very similar again, are the U-type and the J-type. So let's talk about the U-type. U-type is for upper immediate instructions, so like the load upper immediate instruction. It has two operands, the destination register and a 20-bit immediate. And this 20-bit immediate is unsigned. And of course, it has the opcode. Simplicity favors regularity. All instructions have an opcode. So here's an example, load upper immediate. We're going to load this. Remember, this is how this works. At the end of this, after this instruction executes, register S5 is going to have the value A, B, C, D, E in the upper 20 bits, and then it's going to have zeros in the lower 12 bits. So we look at our register table in the earlier slides and see that, well, S5 is actually register 21. We put that into our destination field, RD. Opcode for load upper immediate that we just look up is 55, and then in our immediate field we encode this unsigned immediate, this 20-bit unsigned immediate, A, B, C, D, E. Again, we now put this into binary, and then grab groups of 4. People again try to shortcut and go directly from here to there. Don't do it. The J-type instruction is for jumps, for the jump and link instruction. So this is a J-type instruction. It looks very similar to the for the U-type instruction. To the U-type instruction, it has a destination register and also has a 20-bit immediate field. This 20-bit immediate is, again, kind of bit swizzled with, instead of, just going straight from bits either 19 to 0, it actually goes from 20. It's going to encode an immediate that's from bits 20 to bit 1. So again, we're not encoding bit 0. And again, as always, it has an opcode. All instructions have an opcode. Okay, so let's look at this J-type instruction for jump and link. We actually never use the and link part, but I'll show how to do that right now, where we write PC plus 4, so the address of the next instruction, into some destination register, RD. So here's, up until this point, we've just put JAL func1 or whatever label it is. And that still works. That just means that there is no destination register. No register is written. And actually, really, even though we don't write it like that, this is like saying jump and link X0 func1. So it tries to write to register 0, but we know that register 0 is hardwired to 32 bits of 0. Okay, so, but now we're going to have a destination register, RA. So if, for example, this were at, making up some addresses, we'll say this is in memory an instruction address, I don't know, let's just say hex 10 or something. Here's the address. And there's some encoding. The quote data in memory is actually an instruction. Machine code, 32-bit machine code of the jump and link instruction. But so we have the address of that jump and link is 10, and then we have 14, 18, 1C, 20, 24, 28, and 2C. And so now, even without doing the addresses, we need to figure out, well, the jumps are also relative to the current PC. So PC would be hex 10 when, or hex 10, when that jump and link is executing. So PC says, hey, which instructions is executing? Well, the instruction at address hex 10. Great. So now we need to figure out how many instructions past this jump is the target, or this function 1 or func1 label. So it's 1, 2, 3, 4, 5, 6, 7 instructions past the current instruction or the jump and link instruction. So 7 instructions is, 7 times 4 equals 28 bytes past the current instruction or the jump and link instruction. So we need to encode that 28 here. So the first thing to do is to write 28 using 21 bits. Even though we have a 20-bit immediate, we're going to write it using 21 bits, 0 to 20. Bit 0 to 20. And here we have 28. 16 plus 4 plus 8. It's 28. And now it's going to be the same thing as with our branch instruction. We're going to ignore bit 0. We're not going to encode that in our instruction. Again, this bit 1 is also always going to be 0 for our 32-bit instructions, but we encode that to allow for 16-bit instructions for other applications of RISC-V. So now we're going to need to encode the rest of these bits. And instead of just encoding this directly in the field, do some bit swizzling. And these are this is the bit swizzling. Bit 20 is the most significant bit. Here we go. And then bits 10 to 1 are those next bits. And then bit 11 is the next bit. And then finally bits 19 to 12 to fill out that 20-bit immediate field. But in hardware, when we want to recreate what that offset is, we'll have to put it back into this order, so that we can actually see what that value is. So let's see, it's 28. We'll have to also add a 0 onto the end of that number to actually get the number 28. And then what we would do, well, let's see what would happen. So this is hex 10. This is in hardware. What's going to happen to figure out what that target address is, where it wants to take the jump to, what the next PC should be, right? We want the next PC after the jump instruction to be this add. Right? We want this to be the next PC to be that. So let's see, we had 10, 10, 14, 18, 1C, 20, 24, 28, 2C. So this should be the target address. So how do we get that? Well, we start with the current PC, right? So PC, when the program counter, when the jump and link executes, is going to be hex 10. Well, what's hex 10? That's 16 to the 0, which is 1, 16 to the 1, so that's just 16. And then we'll actually end up adding our 28 bytes away, right? So we're at byte address 16, and we want to jump 28 bytes away. So we're going to add that, and we're going to get 6 plus 8, 14, 2 plus 2, 4, 44. So let's see. So hex 2C, what is hex 2C? Well, this is the 1's place. This is the 16's place. So we have 2 times 16 plus, C times 1, which is plus 12. So we have 32 plus 12. In fact, exactly right. We're going to get 44. Okay, so we're jumping relative to the current PC. So in this case, the current PC was hex 10. I randomly chose that number. No matter what, the distance between here will be 7 instructions. And so that math will work. Okay, so there's our J-type instruction. All of it's pretty straightforward except for this bit swizzling at the end, where we, instead of just encoding, from our perspective, just encoding as immediate 20, bit 20 to bit 1 would make sense. Would still get rid of that 0th bit, no problem. But instead, there's this kind of shifting around of bits for it to make this immediate. Okay, so let's compare these instruction formats. So there were 4 instruction formats. So we're grouping the SB types together and the UJ types together, because the only difference between those are how we treat the immediate field. But let's take a look at why we did some of this bit swizzling. Well, you'll notice the opcode is always in the same place. Well, what principle is that? Well, we have a regular format, so in hardware we'll always be able to know, hey, these 7 bits, these 7 wires, eventually, I know exactly where to find those, the opcode. It's always those 7 wires, those least significant 7 bits of the instruction. RD, if there is one, is always here. RS1 and RS1 is always in this field if there is an RS1. RS2 is always in this field if there is an RS2. And then we can see this is where we started doing some kind of, odd things from our perspective with the immediate. So immediate 11 to 5, that kept the top bits, the most significant bits of the immediate in the same place. And then we put the least significant bits there where RD would have been for the S type. And you'll notice for the B type, well, this is kind of why we did some bit swizzling. Bits 4 to 1 are still in the same place. So eventually these are just, 32 wires coming out telling me some values, high, low, blah, blah, blah. And so if in hardware I can say, oh, hey, these 4 bits will always, ... Bits 4 to 1 will always be in these wires. That helps me. So I don't have to say, well, either these bits, or sometimes I'm going to encode it as these bits, or whatever. We have some regularity in our encoding so that we can say, well, bits 4 to 1 will always be in that location of the instruction if it's an immediate S-type or B-type instruction. Bits 11 to 5 will always be in that location. For this one, we kept some regularity here and kept bits 10 to 5 at least in that location. And for this one, it's a little bit less clear, but bits 19 to 12 were kept in the same location here. And we kept bit 20, the sign bit, in the most significant bit. So justification for, why this kind of semi-confusing encoding of the immediate fields, well, it's because of the hardware. So that we can find the location of our operands in the same place every time when possible. Okay, so we get to design principle 4, which is good design demands good compromises. So, ideally we just have one format of instructions, and then, we have regularity, and just our hardware will be pretty simple. But we actually allow for multiple instruction formats to allow for flexibility. So, for example, add and subtract have 3 register operands, but our add immediate, load word, and store word have 2 registers and a constant or an immediate. And we allow for, multiple, in this case, really 4, 1, 2, 3, 4 formats. But again, remember, these two kind of variations on each of those treat the immediate field in a different way. Okay, but still we adhere to design principles 1 and 2, simplicity in design favors regularity, and smaller is faster, by keeping the number of instruction formats small. So we don't have 10 instruction formats, we really have 4 with, again, variations on the last 2. So let's talk about our constants and immediates again. Remember, load word and store word uses constants as well as add immediate. And again, remember, they're called immediates because, well, now we can see they're immediately available from our instruction. I don't have to go to memory to get them. I don't have to go to register to get them. They're available. They're encoded directly in the instruction. And remember that our load word, store word, and add immediate are using a 12-bit choose complement number. In MIPS it was 16, but in RISC-V it's a 12-bit choose complement number. Okay, so we have our add immediate. Here we have add immediate. Do we need subtract immediate? We've talked about this before. Well, certainly not. We can, right, what could have been done with subtract immediate can be done with add immediate and a negative immediate. In this case, minus 12. Okay, so let's look at how we encode different kinds of immediates. I-type and S-type are the most clear. So again, S-type is for store words, and I-type is for add immediate and load word. And we encode our immediate, our 12-bit immediate. Somehow we have to turn that into a 32-bit value because we're going to add it to, in the case of load word and store word, a base register to get a 32-bit base register to get the final address in memory. Or add immediate, we're going to add it to a source register to then get the addition. So in order to add two numbers together, they have to be the same width. So our 12-bit immediate, we have to then turn into 32 bits. How do we do that? Well, we sign extend it. So we take our bit 11, our most significant bit, and repeat it in the top bits. In this case, in the top 20 bits. Okay, let's look at our B-type, our branch type instructions. Well, again, remember we're encoding a 13-bit immediate in this case instead of 12-bit because we know that least significant bit is going to be 0. So to recreate the 32-bit immediate, we're going to sign extend it. So in this case, sign extend 19 bits, put in our immediate 12 to 1, and then add a 0 into the least significant bit. And then for our U-type instructions, this load up or immediate, again, this is for load up or immediate, we're going to take the unsigned 20-bit value, put that into the upper 20 bits, and then put zeros into the lower 12 bits. For a J-type instruction, we're going to take our, well, actually it's a 21-bit immediate, but it's encoded in 20 bits because we can put that 0 on the end. Basically multiply it by 2. And then we sign extend it. We take immediate bit 20 and put that into the upper bits. Okay, so immediates are, we use immediates in several different ways. Either, simply just sign extending it. And then with our B-type and J-type, we shift it left by 1, multiply it by 2, and then sign extend it. And for U-type, we just take that unsigned 20-bit immediate, put it in the top most significant bits of the immediate, and zeros and the lower bits, the lower 12 bits. So here's a summary of the instructions that we talked about, and I added a couple here, like the and or instructions. But the opcode, they all have an opcode. Some of them have function 3 bits, and even fewer have function 7 bits. And this shows what type that instruction is. So we could also go the other direction, where we're given some machine code and we need to figure out, hey, what's the assembly code for that? What's the assembly instruction for that? So the first thing to do is, so if you're given this, so let's say you're given this hex FDA48393. First thing to do is to write that into into 32 bits of binary. It's tempting to try to go directly from the hexadecimal, but you can't. So don't try. And then we go FDA 4 8 3 9 3. And now we have this kind of collection of bits. We know it's an instruction because we were told that, hey, this is some RISC-V instruction. This is the machine code representation. And now the first thing we're going to do is look at the opcode. So we know that's going to be 7 bits. So we take these 4 bits plus the next 3. So we get our opcode and we say, okay, well, let's see, that's 1 plus 2, 1 plus 2, 3, 4, 8, plus 16. So that's 19. We can go look at our table and say, okay, let's see, or we can even go directly 0, 0, 1, 0, 0, 1, 1. And we can see, oh, here it is. That's an add immediate instruction. And so now we know how to interpret the rest of the fields. So we know it's an I type, because it's an add immediate. So we know what the rest of the fields look like. Okay, so the first thing we do is figure out what the opcode is. And now we know that, hey, the next 5 bits are going to be RD. These 3 bits are going to be the function 3 bits. And then we're going to have 5 bits to tell us what RS1 is. And then finally, those last bits are going to be our immediate field. Okay, so clearly this number here is a negative number. And then we can, write what these are. So this RS1 is 9. RD is 7. And then the F3 field is, function 3 field is 0. So now we can, if we can take the 2's complement of this. I'm actually just going to start here, right, from sign extension. That gives me all the information I need. So I don't have to write so many bits, but you can write them all if you want. 0, 1, 0, 0, 1, 0, 1. So that's the first step, invert the bits. So I'm taking the 2's complement. So I'm inverting the bits. 0, 1, 0, 0, 1, 0, 1. And now we're going to, second step, taking 2's complement, we're going to add 1 to see what that value is. 1 plus 1 is 0. Carry the 1. 1, 1, 0, 0, 1, 0. And so we're going to get, basically 6. 2 plus 4. 8, 16 plus 32. Okay, so the magnitude is 38, and I knew it was a negative number, so that's actually minus 38. Okay, so now I put it together, and I say, okay, this is an add immediate instruction. I know because of what? Because of this opcode. So add immediate, and the function field. So I go back to here and say, well, the ones I've shown you, could only be an add immediate, but verify that the function field is correct. So add immediate, and then we figure out, well, let's see, this was RD is the one I need next. So X7, that's the destination. Here's our RD field. Tell us where the result's supposed to be put in the destination. And then we can go and say, okay, well, what's the next thing? Well, the next thing was the source register. That was register 9. So X9, and then we have our immediate value, which we figured out was minus 38. And then I can go to, I take this, and I go and look at what register 7, register 9 correspond to. Turns out that register 7 is T2, and register 9 is S1. And so I can put those register names in as well. Minus 38. And so, we can see that we can go from, it's basically the opposite process, going from the hexadecimal representation of the machine code, put it into binary, step 1, don't forget to do that. People try to go from the hex, you can't do that. So put it into binary, look at the opcode, step 2, tells you how to interpret the rest of the fields, figure out the field values, write the assembly, and then look up the registers. And there's another example here of, let's see, what's that? The other instruction is subtract. Well, again, it'll be the same process. Start with our hexadecimal, write it into binary, and look at those least significant 7 bits to figure out what the opcode is. In this case, we look at the opcode, it's 011, 0011, and we go look at our list, and we say, oh, yeah, that was for this. So it's definitely R-type. It's either an add, subtract, and, or, right? All of these have the same opcode. So now we need to look at the function 3 bits and the function 7 bits. But we know how to interpret the rest of the fields, at least. So we go in and we can then say, okay, well, I know it's going to be an R-type instruction. And so I parse out the fields, figure out what RD is, and then I can look at the function 3 bits, which are all 0, and the function 7 bits, which are 0, 1, 0, 0, 0, 0, 0. And so then now I go back to my table. I say, okay, they're all 0, so it could be either of these two, but function 7 had 0, 1, 0, 0, 0, 0, 0. Okay, so now I know it's a subtract, and now I can just figure out, well, what are the rest of the fields? I know I can parse out what RD is, RS1, RS2. So we have subtract X7, that's our RD field, X29, RS1, X31, RS2. And then I go look up those registers in the register table, and ends up being subtract T2, T4, and then T6. So you can actually use the simulator to help you just verify some of this. You need to make sure you show all your work, that you do it by hand. But with some of the instructions, you can use the BRISC-V Simulator to help you verify that you did it correctly. But just a warning that the simulator does not convert the following instructions correctly into machine code: the branch of equal and the loads and stores. So load word, store word, load byte, store byte, load half, load byte. And it also doesn't allow you to use these, just the register numbers. So X18, X19, X20 doesn't allow you to do that, but you can just put in the register names. So that's just clearly this is a glitch in the simulator, and then this is just some idiosyncrasy of the simulator itself. So many compilers would allow you to use just the register numbers as well. Okay, so here's an example of how you can use the BRISC-V simulator to help. I put, these ones, the loads, stores, and branch. It doesn't give you the correct machine code for, so just be careful. You just have to definitely do all those ones by hand. You definitely have to do all of them by hand anyway, but you can check. So let's say we load this into our simulator. You can see that, over here that we've loaded it in. And now if you scroll down in the memory, scroll all the way to the bottom, because it's going to load starting with kind of has some preamble code. Boot code is what that would be. But it has some code up at the top, and then it starts loading, the code that we've loaded. So we see our add S2, S3, S4, and this shows the machine code right here, hex 01498933. So here's our machine code. And this happens to be one of the ones I showed you earlier, so you can see that that is correct. The subtract, it does correctly too. Here's our machine code for the next instruction, the subtract. So remember, our memory is growing this way. So you can see the memory location it's located at. So this add is at hex 2C. The next instruction, as expected, is 4 bytes or 4 addresses later, hex 30, and then 34, 38, 3C, and so on. And so, so we can see these instructions, those machine codes over on this left. This is basically the memory contents of these different addresses, which in this case are instructions. But this load word and store word, it fails on. The branch if equal, it fails on. So anyway, but you can use it at least to get started on some of the simpler, like the add, subtract, add immediate instructions. But again, make sure you do it by hand, and only then look at the BRISC-V simulator to get some confirmation, with the caveat that branches, loads, and stores are not done correctly in the simulator.